I start? Okay, well, let's people get installed. It's working? You're sure? Okay. Okay, so good morning. Welcome back for the second lecture. I just remind you where we arrived last time, in the sense that we worked a lot to try to just rewrite the 1D bosonic problem. So for the moment, the Hamiltonian is irrelevant. We're just focusing on the density. And what we managed to obtain is a formula of the density, which relates the density rho of x in terms of a smooth field, or hopefully smooth field, namely a field that can vary smoothly at the scale of the average interparticle distance. So we exclude configurations that are of this shape. And essentially, we obtain this formula where the density is a sum of harmonics here, and we interpreted this formula as a kind of Fourier decomposition of the density, where the first term here is the hydrodynamic term. So think of phi as a displacement from the perfect crystalline position. If phi is equal to 0, all the particles are strictly in a periodic way, and they are exactly at the position you would expect in a crystal. If phi deviates, then the particle will get closer or further apart, so you can really, up to a number, think that phi is just the displacement of the particle compared to their equilibrium position. So it's very similar to an elastic description of a solid. And essentially, we have the Q equal or Q close to 0 harmonic, where you would get a distortion of the density at length scales which are large compared to the lattice spacing, because phi varies only at distance large compared to the lattice spacing. But we have also, if you count the terms p different from 0, you have also much faster varying harmonics. And these harmonics describe the fact that actually, even if the average density at a length scale large compared to the interparticle distance doesn't change, you can change the position of the particles by shifting them right and left in a uniform way. So if I view the density as a density wave, so as a cosine dispersion here, and the sum of all these cosine reproduces a delta function, I can change the phase of this sinusoidal modulation and therefore shift the presence of the particle either right or left at will. And you see that if I do this in a uniform or nearly uniform way on many lattice spacing, the average density doesn't change. I don't bring more particle or push particle away. Nevertheless, the particles are not where you would expect them if phi was 0. Yes?
So the case phi is constant, is special, in a sense, because then we have only harmonic decomposition and nothing, no variation. What is the physical significance of phi constant then?
So phi constant means, so if phi becomes a number, doesn't fluctuate, what you have is that your density becomes a number and is perfectly ordered. So it would mean any number. I can take phi, which takes any value. Then it means my density has perfectly ordered, or at least has acquired an average value, which is given by this expression, which is above. Okay? So if I had a crystalline or near crystalline or whatever phase, it means phi would acquire an average value. Constant is just one special case, and phi equal constant means I have a perfect crystal of bosons. Okay. My bosons are not superfluid or what you have. They just crystallize. One is here, one is here, one is here, one is here, and they form a perfectly periodic array of particles. I mean, I don't know what is the initial. Here there is no time or whatever. I can position this crystal where I want by choosing phi. So phi is just the position of one particle in the crystal if phi is strictly constant. But if phi is a number, it means I will have a classical and fixed average of the density, which is given by this expression. Of course, phi is an operator. It's something which fluctuates and is driven by an Hamiltonian, which we will write. So whether the density has deviation from the average value in average, that's another story. We'll discuss it in a moment. Are there other questions? By the way, I ask you to do two exercises. So did someone, before we move forward, did someone do the first exercise? The second was a little bit more nasty. The exercise saying what would happen if I was writing for fermions the interactions under the form rho j minus 1, where rho j is rho j up plus rho j down. Well, what do you mean nothing happened? So it's the same Hubbard model, then the one plus a chemical potential term. So just to tell you, if you write rho j up plus rho j down, just very rapidly, times rho j up plus rho j down. The minus 1 goes in the chemical potential, so that's not a problem. And then what happens to the term rho j up, it's C dagger j up, C dagger j up, C j up. And then you can use the anti-commutation relation between these two. This is 1 minus C dagger C. Then the term which has 2C close by is annihilated. So this term is actually just rho j up. So you get rho j up plus rho j down plus 2 rho j up, rho j down, which means if you remove, sorry, there was a factor of 2 here. If you remove the factor of 2, you find exactly the Hubbard model. It's, of course, not the same if the interaction is not on-site. If you have nearest neighbor or next nearest neighbor or whatever, then you have to worry about writing the interaction in a proper way. Why do I ask that? Because this way is manifestly spin rotation invariant. When you write something like this, it sounds like you have chosen a quantization axis. So apparently, it's not spin rotation invariant. I have to know what Z is, what SZ is. So if I change the axis, potentially, I could get different result. But in fact, this term is fully spin rotationally invariant because it's a contact term and you have fermions. If you had bosons, this term would be nonsense. I mean, would break the spin rotation symmetry. For the second exercise, we'll come back to it in a moment. Okay, so sorry for this going in and out, but I thought it was useful to discuss the solution of the exercise. Okay, so we get this expression for the density. Now, we would like what is missing. So we have a dictionary. If you give me the density in terms of the original particle, I can find my field phi and vice versa. Now, we need something else, and then we will be able to express any operator in terms of the new variables. I need to express the single particle operator itself. So for expressing the single particle operator, we started to write the formula. We write that this is the square root of the density, and then I need to put a phase. And so I say this is exponential of I theta of x, where theta of x is essentially the phase, so it defines the operator theta of x. Now, of course, I have these two fields and I don't know what they are doing, but I can use the fact that I know that psi of x, psi dagger of x prime, is essentially delta of x minus x prime. So psi of x and psi of x prime have very precise commutation relation. So I can use this to extract the commutation relation between phi and theta. Because you see that if phi and theta commute, for example, with the expression I've written, there is no way I'm going to get the right commutation relation between psi and psi dagger. So I let you do it as an exercise. It's not foolproof in the sense that you have to, let's say, do it in reverse, but I let you show that phi of x and 1 over pi grad theta of x prime are essentially canonically conjugate variables. So this is I delta of x minus x prime. So if you prefer, 1 over pi grad theta is the momentum conjugate to phi at point x. So this variable theta and phi not independent variable. They are not numbers. They need to satisfy a very precise commutation relation because of the original commutation relation between the single particle bosonic operator. So it's easy to check that if you take the expression I have given, it takes a little bit of time, that's why I don't want to do it here, but it's easy to check that if you take this commutation relation and then you compute explicitly this object by using the definition of the density and blah, 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 and the rule of commutation of two exponential, you know, the exponential A, exponential B is exponential B, exponential A, exponential of the commutator of A and B. If A and B commute with their commutator and blah, 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 you end up with a precise and correct commutation relation between the operators. Okay, so we are all set now. We have a dictionary. We didn't solve the problem. We just wrote a dictionary. So now if you give me any super complicated operator in terms of the original bosons, I know how to write it because I know how to write any operator of bosons in terms of the single particle operators using standard second quantization rules. If you give me any operator in terms of bosons, I can write it in terms of my phi and theta. Okay? So we have a phase. As I said, phi of x is associated with a density fluctuation. And I would say theta of x is associated with a superfluid fluctuations, whatever that means. Meaning, if theta was a number, if theta is ordered, my system is a superfluid. Because then my function, my single particle operator for bosons has an average value. If I say theta is a number, let's say theta 0, then the average of psi is essentially rho 0, at least rho 0 will survive, exponential of I theta 0, and that's the signature of superfluidity. When the average of a bosonic, of the creation of or destruction of a boson as an average, it means all the particles condensed in a macroscopic state. Yeah.
So in a sense, all this machinery relies on the two manifest or the clear manifestations of what, like crystal or superfluid, in a sense. So like the two, in a sense, yeah, perfect, like show-ups in the theory, right?
So actually, actually you will see that these are the two orders which are competing. Okay, so this will come. But I would say this machinery relies on one thing which is crucial, which maybe was not totally apparent when I did the derivation, and I can recommend for a generalization to higher dimension. So this is a paper together with Pierre Le Dussal, and this is Phys. B, and this is 1995. I will write the precise reference, but it doesn't matter. So the thing it relies on is the fact that in 1D, you can always order the particle unambiguously. And, you know, you start from the left, and then you move to the right, and you can say, this is particle 1, this is particle 2, this is particle 3. And you will tell me, what happens if they cross? If they cross, they are indiscernible. You don't care. You just say the one which is there is still particle 1. The one which is more on the right is still particle 2. And you cannot make the difference. If you're in more than one dimension, you cannot use this trick, because depending on the path you will follow, you will get different numbering for the particles. In particular, in a crystal, you know very well that if you have a dislocation, if you have a defect, a topological defect, then the number of the particle depends on how you go around this defect. And then you cannot find a way to write this wonderful formula, which one can generalize in higher dimension by saying that you sum over the vector of the reciprocal lattice of the crystal. So the thing which is making this formula work is the fact that in 1D, it doesn't matter how many particle can cross and uncross and whatever, you can, at a given time, always say 1, 2, 3, 4, 5, 6, 7, and so on. And therefore, the field here can be made smooth, unless you pile up particle on the same side. In 3D, let's say, or 2D, defining this field is simply not possible in a non-ambiguous way. It's only possible if the particles form a crystal. If they form a nice crystal without topological defect, then you know the coordinates of the particle in the crystal, and then you can generalize this formula. So if I want to quantum crystal in 2D or 3D, I can do the generalization of this, and this is an extraordinarily useful formula. I mean, the generalized formula in higher dimension, allowed to solve a certain number of problems, in particular for disordered quantum crystals. But in 1D, it always works. Okay, so, yeah. I'll come to fermions in half an hour. So it works for fermions, it works with spins, it works with anything. That's a good question. I should have retracted. I don't know if it works with particles with non-abelian statistics, but I suspect it should work as well. You just attach some equivalent of a flux tube to the particle. You do a Jordan-Wigner transformation. But I won't sign with my blood for particles with non-abelian statistics. I think if you want to define clearly particle with non-abelian statistics, technically you need to be in 2D. Because, you see, in 1D, in a way, you cannot dissociate the statistics from the interaction. If you want to exchange two particles, they have to cross. So we'll come to it in a moment. Bosons with infinite repulsion are not that different from fermions. Not really. Let's come back to this. So again, for particle with non-abelian statistics, I would not swear it, but I can swear that this method will work for spins and fermions, guaranteed. And we'll do it explicitly in the course. The space-time is a little bit different. Again, if particle braid, it doesn't matter. Certainly if there are bosons or fermions, I can again say this is 1 and 2. I don't need to braid them. I just say I go back with the index for the particle which is on the leftmost side or the rightmost side. And I strongly suspect you can do similar things with fractional statistics, but that's an excellent question, and I don't know the answer to this one. But yes, it worked for at least the two other conventional particle you can. There was another question, I think. No? No? Okay. So now let's try to use our dictionary on one observable, which is nice, which is the Hamiltonian. Okay? After all, we did all this. We did all this because we needed to solve this problem of interacting bosons. So let's start with the Hamiltonian. I rewrite it. 1 over 2m, sum over dx, grad psi dagger, grad psi. No, before I do the Hamiltonian, let me write maybe the complete formula. Okay, because you could say, oh, it's ugly what you did here. There is a square root of the density. Well, let me write cleanly the square root of the density. So let me write cleanly, let's say, psi dagger of x, which is again square root of rho of x, 1/2 exponential of minus I theta of x. Now, what is the square root of the density? I remind you that initially the density was a bunch of delta function. So the square root of a delta function is a bunch of delta function with a normalization which is ugly. Because, okay. So actually the square root of the density is essentially the density. Up to a normalization, yes? No, they don't commute. So at the same point they will commute. At the same point they will commute. So it doesn't really matter. But you're right, I could be cleaner and write it. So actually, you can work out this thing by integrating, and you can always choose the 0 of the integration, so that the commutator of theta and rho, which is the integral of a delta function, which becomes a theta function, you shift it to make the sine function. It's a very good question. So you want phi of x, I want phi of x, and theta of x commutator at the same point to be 0. And I can always do this. Okay? You're perfectly correct. Okay, so what I'm saying is that this is essentially up to normalization. This is essentially rho of x exponential of minus I theta of x. And we'll come to the normalization in a moment. So I just want to say you can even remove the square root. You can keep it if you like it, but because it's taking the square root of something which is either 0 or infinity, the square root of 0 or infinity is 0 or infinity. So it's a delta function at the same position than before. So I can do the same decomposition than before and get essentially the density. Yep. Yes. Yes. So I shouldn't have written this. And again, I'll make it more precise in a second when you compute the correlation function. So maybe what I should say is that if you want something which is suitably normalized, I would say I have something which starts with rho to the 1/2 exponential of minus I theta of x. I get a term which is minus 1 over pi grad phi of x, 1 over 2 pi grad phi of x exponential of minus I theta of x, which would be doing the expansion, which would be doing the expansion of the square root here. So if I do the expansion of the square root by assuming this is small, this is rho 0 to the 1/2 minus 1 over pi, blah, 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 and I should divide properly by rho 0. We are doing a lot of effort for something that I will blast in 2 minutes later, because I will tell you that any correlation you compute, you don't know the amplitude. So we could do the expansion. So let me do it properly. So I would say I would get rho 0 minus 1 over pi grad phi to the power 1/2 exponential of minus I theta of x. And then I would say I would get the sum with p different from 0. And then I forget the square root, because I say this is a bunch of delta function, 2p pi rho 0 minus phi of x times exponential of minus I theta of x. The point I want to make is that there are, again, several harmonics in the density, and here I would just put the rho 0 to the 1/2 for simplicity to respect the dimension. But again, the prefactors, the things which are in front here, as we will discuss, I don't know what they are. So take this expression in big quotes for the moment. We'll make it more precise later. Okay, let me go back to the Hamiltonian. So if I go back to the Hamiltonian, well, let's try to flex our muscles and compute first the term which is 1 over 2m. Then I get sum over dx, grad psi dagger, grad psi over 2m. Okay, so I just use the fact that psi of x is rho 0 to the rho to the 1/2, rho of x. Again, I put twice the mass. I'm not awake. So psi of x is this. So if I take the gradient of psi, this is the gradient of rho 0 to the 1/2. So this is 1 over rho of x to the 1/2. There is probably a 2. There is a grad rho of x. There is an exponential of I theta of x. And then I get plus rho of x to the 1/2. I get exponential of I theta of x, and I get I grad theta. So when I multiply this by grad psi dagger, what I get, the exponential of I theta factorized, so they cancel, and then I have a term which is real, a term which is purely imaginary, so I get the modulus square. So what I will get is grad rho square divided by 4 rho of x, and that's it. And then I will get plus rho of x grad theta square. So you see the kinetic energy as a relatively simple expression in terms of the phi and theta. And now I have a problem because rho is horrendously complicated. So what do I do? Well, I will use high velocity and waving arguments, and I will tell the following. I will tell in this derivative, I have several terms. I have the derivative of rho 0, which, okay, goes away. I have the term which is minus 1 over pi grad phi, which is smoothly varying at the scale of the lattice spacing, which I have to keep. And then I will have terms that will be derivatives of terms of the form sum over p exponential of I 2p pi rho 0x minus phi of x multiplied, when I differentiate this, multiply by factors like grad phi, by 2 pi, by whatever. And then I integrate this over x, because in the Hamiltonian I integrate. Now, all fields vary smoothly, and I have here something that oscillates like crazy if p is different from 0. So the claim would be everything which contains oscillations will cancel when I will do the integral, or will be less relevant, or I can throw it away because I don't know what to do with it. Whatever is your degree of rigor, but I'll throw them away. And the rationale is I'll throw them away because if I have a smooth field which is multiplied by a rapidly oscillating factor, that's even a math theorem if you do it properly, the integral tends to 0 when the period of oscillation tends to, when the period of oscillation tends to 0. In a way, you have a smooth field, you get an oscillating factor, the positive part of the integral compensates the negative part of the integral, and then you integrate essentially the derivative of the smooth field, and the integral for derivative with suitable boundary condition is 0. So it's not a theorem, it's not clean what I'm doing. You're right to crucify me if you don't like it, but I'll do it nevertheless, and we'll come back to this later. So I hope you have a list of all the lies that I'm telling you and all the things that I make you swallow for the moment, because you have to make me pay for it. You have to make me then say, oh yeah, but remember here what you did? Why? And I'll try then to be honest at the end of the lecture or during the lecture by unwinding all the lies and all the things that I made you swallow. But that's part of the game. We don't know really what to do with these terms. They are nasty, but there is the idea that maybe they oscillate, we can get rid of them, so let's get rid of them and see what we get. Okay? So if I do this, then the gradient of rho is essentially the gradient of rho 0 minus 1 over pi grad phi, because I just keep the term with p equals 0, no oscillations. So if I do this, I get minus 1 over pi, the second derivative of phi. So at the end of the day, my kinetic energy is the integral over dx of a term which is, and again, I will do a drastic simplification. Rho of x here is made of a lot of oscillating terms, so I throw them away. And then I'm left with rho 0 minus 1 over pi grad phi. Well, again, if I integrate something which contains a grad phi, I can probably get rid, or I will say it contains more derivative than this one, so this is less relevant, so I will throw away this term and just keep rho 0 here in front of the grad theta square. So I will write that my kinetic energy is rho 0 grad theta square, and then I get another term, which is 1 over 4 rho of x. So same thing. I will say this is 1 over 4 rho 0. And I get now 1 over pi square. So it must be going there. Nabla square phi square. And now you see I have a very nice Hamiltonian. I liked it. It's very beautiful. It's nice. Why is it nice? Well, it's nice because essentially, remember that I told you that 1 over pi grad theta is the momentum conjugate to phi. So what I've written here for you, H kinetic, is the integral over dx of something which is rho 0, and there is a 1 over 2m here, probably, in front of all this. This time it's there, times pi, the number, and then pi phi square, plus 1 over 4 rho 0 pi square, and I probably screwed up in the prefactors, but it doesn't matter at that stage. And now it's an Hamiltonian that I like, because it's an harmonic oscillator Hamiltonian. Yep.
So throwing away the rapid oscillating terms, how to not reduce the singularity of the delta functions that in effect produce them?
Welcome to the oscillating term. So for the moment, let's try to see whether this one makes sense, and we'll come back to the oscillating terms. Okay, so I can go essentially and solve this model. I can go to Fourier space. I can write an action. So this is as usual. If you want to write, oops, voila. This is the cubic version of an action. So if I want to write an action, I will write that this is the integral of I pi phi dot minus the Hamiltonian, which is a function of pi and phi. And essentially, I need to trace out the field pi and do it properly. I'll try to do it properly. Be gentle with me if I screwed up in getting the right factors. So the action is, let's say, we have something which is sum over dx, okay, which doesn't matter. We have rho 0 pi square. We have pi square here. Then we get plus I pi phi dot. And plus blah, 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 which doesn't matter at that stage. So this is rho 0 pi square times pi plus I phi dot divided by rho 0 pi square, and I have probably a factor of 2 here. And then if I do this, I have to add a term, which is phi dot square, and then I would get rho 0 pi square, and in the denominator, I would get 4 rho 0 square pi to the 4. So I can trace out the terms. So my action is simply the integral over dx. Now I get phi dot square. I do it in imaginary time. So this is the imaginary time action. So dx, d tau, and so on. Then I get pi square. So this gives me 1 over pi square here. I get rho 0, it gives me 1 over rho 0, and I get my factor of 4. And I shouldn't forget the second term, which is plus 1 over 4 rho 0 pi square, and I get grad square phi square. And there was a 1 over 2m that I forgot. There was a 1 over 2m here, which was here. So I have a 2m here. So I have a 2m here. And therefore, I should put my 2m here. And therefore, I'm left with a 2m in the numerator here. Okay. So at the end of the day, my action is 1 over 4 pi square rho 0, which factorizes. I get sum over dx d tau. I get something like 2m times phi dot square plus nabla square phi square. And now if I go to Fourier space, this thing is simply 1 over 4 pi square rho 0 times sum of dq d omega n, where these are the Matsubara frequency. I can do it in real time, but it doesn't matter. This is 2m omega n square plus k square square, so k to the 4 times, so this is, sorry, and I should put the field, phi star k omega phi k omega plus k to the 4 phi star k omega phi k omega. So at the end of the day, I have a very nice quadratic Hamiltonian, so this is tk d omega n, with something which is 2m omega n square plus k to the 4 times phi star k omega phi k omega. And I have a prefactor here, which is 4 pi square rho 0. So this is the kinetic energy. Now, am I happy with this result? If I look at the eigenmodes, if you want, well, I can go back to real space. I change omega n to I omega. And so I see that I get modes which propagate with a frequency omega, which is not proportional, but which is equal to k, or omega square, which is proportional to k to the 4 over 2m. And I probably screwed up because I forgot 1 over 2m elsewhere. Yes, the 1 over 2m was in front of this one. So there is a 2m here also. There is a 1 over 2m here. And there is a 1 over 2m here. So this is 2m square. And so you see that I have modes which have a frequency which is k square over 2m. Wonderful. I've recovered the spectra of free bosons. That's wonderful. All 2 hours of efforts to just recover that the frequency is k square over 2m. But at least it tells us that it might be not totally crazy to do the things I did, throwing away the oscillating terms and whatever, because I cover that at least my eigenmodes, sorry, this is not H, this is S kin. So this is one half of mv2, the velocity square, and this is the energy of my bosons, which gives me back my kinetic energy. So I'm super happy because at least it sounds reasonable. I started with the Hamiltonian of free bosons whose eigenvalues were energy is equal to k square over 2m, and after all this complicated transformation, I go back to exactly the same thing. Now, the second part, the interactions. Okay? That was the problem in the single particle language. The interaction term is a nightmare. So let's write the, action, if you want, for the interaction. This is the integral of dx d tau of rho of x and tau times rho of x and tau minus 1. I, again, get rid of this. It's in the, and let's say this is, I subtract the average value to really look at the fluctuations. And I will put here a factor of u. I can put u over 2, it doesn't matter. Okay, now I use my dictionary, and I use the same prescription. I throw away the oscillating term. But now my rho is rho 0 minus 1 over pi grad phi. So you see that the interaction action is u over 2 times the integral over dx. This first term is minus 1 over pi grad phi. The other term is minus 1 over pi grad phi. So I get minus 1 over pi square grad phi square. So at the end of the day, my total action is something like, okay, a prefactor which I hope I got right, but I don't really care. Something like sum over dx d tau times 2m, let's say, phi dot square plus 1 over 2m grad square phi square. That was my kinetic energy. And then I get a term which is u over 2 pi square grad phi square. And now what can I say? I'm able to fully solve the interacting problem. My Hamiltonian is as quadratic with the interaction as it is with just the kinetic energy. So with this change of variable, I can solve the interacting problem without any effort. This thing which was unsolvable, not unsolvable because Lieb and Lillinger solved it, but which was so complicated to solve in the original single particle basis, is essentially very naturally quadratic if I write it in terms of the smooth field phi and theta, and throw the harmonics. Of course, I have all these harmonics that are polluting me and make the Hamiltonian very complicated. But now I have a good argument, or at least a reasonable argument, to say that I can neglect them. They oscillate. They are less relevant. I can throw them away. I have a way to organize what I think are the important terms in my Hamiltonian. Okay? So now if you look at this Hamiltonian, it's totally quadratic. This will give omega square. This is k to the 4, so this is what was giving the kinetic energy. But now you see that we have a term which contains actually less derivative than the ones in the kinetic energy, so which will be more relevant, which will control more the low energy physics than the term coming from the kinetic energy here. So actually, it also tells you that as soon as you will put any interaction among the bosons, you will completely change their physical behavior. You will change the spectrum. So let's write the spectrum. So if I go to Fourier space, if I'm going, oh, so there, this is not in factor of everybody. So this is plus sum of dx theta. So if I write the spectrum, what will I get? I'm not writing the constants because they are not important at that stage. Trum. I will have minus omega square coming from this term times some constant. I will get a term which is alpha k to the 4. And then I will get another term here, which is a constant that I'm not writing here, times u. I keep the interaction to remember. And then I will get k square here. So it means that my eigenenergies are omega is square root of alpha k to the 4 plus a term u, k square with a constant c here. It's not the speed of light, it's just a constant. And you see now what happens. This term here tells you that the spectrum is modified compared to non-interacting bosons. Non-interacting bosons, I had a spectrum of excitation which was epsilon k was going as k square. And now, because of the interaction, I get essentially, doesn't want to let me change color for some reason. I get essentially a spectrum which is probably very close to the old one, but at some point is dominated by omega proportional to k. Here, omega is proportional to k square. So the interaction, when they are present, completely transform the spectrum, give you a linear spectrum at low momentum instead of the quadratic spectrum. For people who have worked out the Bogolyubov solution of a normal superfluid in 3D, this is exactly the expression for the Bogolyubov energy. Yeah.
Does it make sense to introduce a healing length then here?
So here you can introduce the equivalent of the healing length, and we'll discuss it when we talk about ultraviolet cutoff. So there is the equivalent of a healing length. Yeah. But I just want to emphasize at that stage that this spectrum would give you exactly what you would expect from Bogolyubov theory. So at that point you could say, oh, I reproduced the Bogolyubov spectrum, so what? I could have done it by Bogolyubov. Yes, but of course, what we will see after the break is that the correlation functions are not the same. And that's the main point. Now we have a dictionary which allows us not only to get the spectrum, but to get the correlation functions. So essentially, you see that now we have a tool which is extremely powerful. We solved essentially this Hamiltonian in 2 lines. We have the Hamiltonian under a quadratic form. So I would say at low energy, actually this term is not important. So I can even throw it away if I want. So there are 2 possibilities. If I want to describe the low energy properties, I can keep only the most relevant operator, which is u times grad phi square, meaning I throw away the grad square phi, which will give me a subdominant contribution. But of course, if I do this, I have to remember that I need a cutoff on K, because this is not valid all over the place. This is valid up to a certain point. So if I take an Hamiltonian where I consider that my spectrum is strictly linear, that frequency is proportional to K, it's not valid above a certain energy here, which will depend on the interaction, which will depend on the density, which will depend on the mass, and so on. So I will say, let me focus on the low energy part, but then I need an ultraviolet cutoff, not to screw up by considering that this spectrum extends to infinity, in which case I might even get integrals which are divergent or ill-defined or whatever. So I will put a cutoff on K, which I will call lambda. But if I do this, you see that our Hamiltonian is essentially a term, or action, is essentially something that contains a phi dot square, or a pi square, momentum square, and then a term which is grad phi square. So let me write the Hamiltonian in a generic form. So I will write it as 1 over 2 pi. And then I only need two coefficients. So I have one first coefficient which I write this way, u times k. Pi is the number, this is the operator, square, plus u over k times grad phi square. So these coefficients have been written in a way which makes apparent their units, their dimensionality. So I just have an Hamiltonian with two terms. So I just need one coefficient here, one coefficient there, which I choose to write as the product here of two numbers and the ratio here of two numbers. This things u as the dimension of a velocity. And if you do the exercise of working out precisely the spectrum with this, you will find that omega is equal to uk. So u is actually the sound velocity. Why the sound velocity? Because phi controls the density oscillations, and the way density oscillation waves propagate is the sound. When I'm talking to you, I'm making density waves in the room, and that's the way the sound propagates. And k is a dimensionless parameter. These parameters, they got a name. They are called Tomonaga, and we'll come to it. Tomonaga-Luttinger parameters. So k has no dimension. It's a number, 3, whatever. You see that if I trust my calculation, I would say that essentially, let's go back to something which is a little bit simpler, which is the starting point. And there is a 1 over 2m here. The coefficient here is rho 0 pi square over 2m. So I have rho 0 over 2m, which is the product u times k. U times k is rho 0 over 2m. And essentially, the ratio u over k is essentially, and I probably screw up with factors of pi, I don't think it's really important. So u times k is pi rho 0 over m, because this is u times k divided by 1 over 2 pi. So this is 1 over 2 pi. U over k divided by 1 over 2 pi is u, if I take this, is u over 2 pi square. U, the interaction, not the velocity, over 2 pi square. So if I want k, I would say I do the ratio of these two numbers. So k is behaving as 1 over square root of u, and the velocity u is behaving essentially as square root of the interaction. So the lower the interaction, the more flat is the velocity here. And of course, if the interaction goes to 0, not only this cutoff goes to 0, but of course the velocity becomes 0. But if the interaction is finite, I get a part of the spectrum which is strictly linear. And that's good. We would like this to happen because we know in 3D, in a superfluid, this is what Bogolyubov tells us. Okay, so we are happy with that. This other number, k, well, it is what it is. And we don't know what it is used, but we will see that after the break. Okay? Because now we have something very potential to do, which is, okay, now we have the Hamiltonian. We know how to diagonalize the Hamiltonian because the Hamiltonian, or the action in Fourier space, is just 1 over 2 pi k sum over dq d omega n. And then this is 1 over u times omega n square plus u k square times phi star q, sorry, this is phi star k omega n, phi k omega n. And then we are back to the tutorial that you got on the free Gaussian field. And now we know that how to trivially compute all the correlation functions. So this is what we will do after the break. I will give you the result. It's simpler. But after the break, we will compute the correlation functions. So the first thing to compute is, of course, the average of the bosonic field, psi of x and tau, to know if we have a true superfluid. But then we can compute psi of x and tau, psi dagger of 0, 0, which consists in creating a particle at point 0 times 0 and destroying it at point x and time t. And we can compute the fluctuations of the density, rho of x and tau minus rho 0 times rho of 0, 0 minus rho 0. And these three correlation functions will give us information on the physics of our system. And you see, again, this is a miracle. I don't know if there are people who sweated here the Liebling solution of the Bose gas. It's not a piece of cake. I mean, you have to work seriously hard. Here, if you have the dictionary of bosonization, for which you have to work seriously hard to get, but once you get it, solving the interacting problem is literally 3 lines. Of course, you could say, yeah, but it's dirty, you didn't do it right because you threw away a lot of terms or whatever. So let's go back to that after, but first, let's explore the solution. I think it's a good point to make the break. And I'll stop here and we reconvene in whatever, 10 minutes or something like this. They are coming back, they are coming back. Yeah, sure, but I think we should restart because yeah, go ahead.
So like in 1D lattice, we have Jordan-Wigner.
Yes.
And in this case, you have a factorization. So is it possible to take some component limit to connect with 2 different lasers?
You can do Jordan-Wigner. I will do it to go from the bosons to the fermions.
On lattice or on field theory?
It doesn't matter. Both is the same.
How do we define on the field theory? Because the Jordan-Wigner is a Pauli string.
It's the integral from minus infinity to x of the Okay, I think we should restart slowly. Okay, let's go for the calculation of the correlation functions. So the first one, okay, I won't do all the calculations because they were all done by Jérôme last week in the tutorial on the free Gaussian field. Again, we have an Hamiltonian here that is just a Gaussian field, and the only thing we need to compute are either linear function or exponentials of the Gaussian fields. So this is just application of the formulas that you will find in the notes that you were given last week. I'll just show you one of the calculations. It's not the most complicated that you can do. So let's do this one, which is the phi of x and tau. And of course, I mean the time-ordered one, from which you can extract the retarded and so on. So I compute phi of x and tau minus phi of 0, 0 square. So this is simply the sum over q and omega of exponential of I will write it that way, k scalar r, where k is q omega, r is x and tau, minus 1 times phi of k, and this is square. And so at the end of the day, this is the sum over k1, k2 of exponential of I k1r minus 1 exponential of I k2r minus 1 times phi k1 phi k2. Now I can take here, because the field phi is real, I can take phi star of minus k1, and I have to take the quantum average of this. And the propagator of this up to constants, because the Hamiltonian is quadratic, is something like k divided by omega n square plus q square. And again, there is the velocity which is popping up in this expression in some way. So there are coefficients here which depends on the velocity to make the dimension correct. But you see, and of course, delta k1, k2. So at the end of the day, this integral is essentially k, sum over k1 of exponential of I k1r minus 1, exponential of I k2r minus 1, and then I get something which is 1 over omega n square plus q square, which is indeed modulus of k square. Sorry, there is a minus here, and this is k1 again. So at the end of the day, I get a sum over q and omega of something which is like k, which is 2 times 1 minus cosine qx plus omega n tau. It's not exactly that, but it doesn't really matter at that stage. Omega n square plus q square. Now you see that this is a two-dimensional integral. This is dq d omega. This is behaving as 1 over q square, so the integral is logarithmically divergent at small q and omega, but it's regularized here because at small q and omega, the cosine will be 1, so this prevents the divergence. So essentially, there is a logarithmic divergence, which will be controlled by the fact that x and tau are finite. When you do the integral, what you will find is something which is k times log of x square plus absolute value of tau plus something which I call alpha square divided by alpha square. And I will explain what it is. So what is this alpha? Well, remember I told you I should remember that this linear spectrum, omega proportional to q, doesn't extend to infinity. So I should put here in the integral a cutoff exponential of minus q over lambda to cut the large value of q. Otherwise, my integral would be logarithmically divergent also at large q. 1 over x squared is divergent not only at small x, if I have a two-dimensional integral, but it's also logarithmically divergent at large x. The divergent at small x is physical. It's controlled by the finiteness of x and tau. But the divergence at large q is not there. It's because I approximated my spectrum by just omega square is proportional to q square. If you remember, there was a term q4 in the original spectrum, and now this regularizes the integral as large q. But if I forget this term by saying for small q, q4 is negligible compared to q2, of course, I will get unphysical divergence at large q. So to cure this unphysical divergence, I should put a cutoff at large Q, and what I call alpha is essentially 1 over lambda, is 1 over the cutoff. So think about alpha as a kind of short distance cutoff, a lattice spacing, a distance between particles below which this continuum description is not valid. So alpha here is of the order of 1 over lambda, and again, it's lattice spacing. It's a cutoff which is dependent also on the interaction. Sometimes people call this the healing length for superfluid, for weakly interacting superfluid. It doesn't matter at that stage. There is a cutoff. I need to put it. I could take the full spectrum, Q squared plus Q4, but then the integral would be slightly more complicated to do. Yep.
So could you slide up?
Yep. Up or down? Yeah, down.
In this first expression, I was still lacking the average, or if it is or...
So the average is here. This is the quantum average. Quantum average. Here it's missing. You're absolutely correct. So here it should be equal average, average. And then the only thing I need to quantum average are the fields. These are numbers. This is just the Fourier transform of the difference of the field. So if I express this difference in terms of the Fourier transform, so this is what I get. And then if I just expand the square, I get sum over K1, K2. I need to put 2 indices here, and then I get the product of phi K1, phi K2. But I use the fact that because phi is real, phi star K1 is equal to phi minus K1, and then I just need to do this quantum average. Now, to do this quantum average, I use the fact that my Hamiltonian is Gaussian. So the average of the product is just the inverse of the coefficient, which is in the Hamiltonian, which is essentially this one. And there is a delta function because my Hamiltonian is diagonal, so minus K1 has to be equal to.
And I was still missing a Q, like on the line.
Q. So what I call K, so what I call K is essentially Q and omega. So K is a two-dimensional variable here, which represent both space and time. Fourier. Yeah, it's a two-dimensional vector. Okay. Okay. So this is essentially the one of the most useful correlation. Let me give you another one. If I have exponential of I phi of x and tau, exponential of minus I phi of 0, 0, then it's easy to show that you get this, which is 1/2 of the average of phi of x and tau minus phi of 0, 0 square. And then this is exponential of minus k over 2 log of blah, blah, blah. So you see that if I compute coefficients here of exponential of the field, what I get at the end is something which will be a power law with here a power which is k over 2 of something which is alpha square divided by, blah, 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 blah. There is k, yeah, okay, doesn't matter. Let me put k over 2 here. So this is k over 2 of alpha divided by square root of x square plus, I will write it tau square. I should write it y square technically to avoid the divergence, y square. So y is essentially absolute value of tau plus alpha, otherwise you would be worried. The point I want to make is that, again, not worrying about coefficients and precise values, you can find this in the notes and the reference I gave you. This thing here turns out to be a power law whose power will be controlled by the number k, this dimensionless number that I was mentioning. This is a power law which is here for this correlation isotropic in space and time. So this is essentially something which is, of course, where time as the dimension as the same plays the same role than space here. And again, it has a prefactor which is depending on the cutoff. So something I don't know really well. I mean, here I can do the calculation, but I'm just saying this cutoff has been put a little bit by hand. So essentially, the message is that I will get a power law correlation this is controlled by k. And I have a prefactor which is highly non-universal. By that, I mean that the prefactor depends on the cutoff procedure. Okay, and now I'm ready to give you the correlation functions. So let's start by the density-density correlation, which is perhaps the simplest to see. So you see that rho of x and tau minus rho 0 starts as 1 over pi grad phi. Okay? And then I have the higher harmonics. So again, I want to classify a little bit the things. So let me classify them by saying I will get first rho 0 exponential of I 2 pi rho 0 x minus 2 phi of x. Then I would get another term which is rho 0 exponential of I 4 pi rho 0 x minus 4 phi of x. And then I can continue. And of course, I get the minus sign and whatever. Okay. So now I need to multiply this horrible series with itself and do the correlation. So I will get the grad phi first. So I will get a term. So the average of delta rho x tau delta rho 0, 0 is essentially 1 over pi square, the average of grad phi. Then I will get terms where I will have exponential of I 2 pi rho 0 x, exponential of I 2 phi multiplied by its corresponding term on the other side. So I will get something like plus exponential, so rho 0 square, exponential of I 2 pi rho 0 x, average of exponential of I 2 phi of x and tau, there should be a minus here, exponential of I 2 phi of 0, 0. And then I could get the rho 0 square, exponential of I 4 pi rho 0 x, with the same thing, but this time with an exponential of minus I 4 phi x tau, exponential of I 4 phi 0, 0, and so on. And you will tell me, what about the terms which would be the cross terms, like terms like exponential of I 2 phi, exponential of I 4 phi. I'll let you do as an exercise that these terms are strictly 0. They are strictly 0 because they will be exponential of minus a constant times sum over q and omega, 1 over q square plus omega square, which is divergent. And then this is exponential of minus infinity, and this is 0. So the only thing here that makes this integral convergent is because the coefficients, oops, sorry, I should bring it back, is because these two numbers, here and here, are strictly opposite. If I get something which is modulus 1 here, minus 1, it gives me the 1 minus cosine, and I regularize the integral at small q and omega. Imagine I put 1/2 here, then this thing would tend to 1/2 when when q and omega tends to 0, and I would get an integral which is hopelessly divergent. In the analogy between this Gaussian field and charges, you can view the coefficient in front of phi as the electric charge. And I only get non-zero correlation if my system is globally neutral. I need as many positive charge as I need negative charge. So here, I would try to compute correlations in a system which would have positive charge 2 and positive charge 4, and this is 0. 0 because of the fluctuations, because of the integral on the Gaussian field. Yeah?
Since we threw away the rapidly oscillating terms in Hamiltonian,
Yes.
I think there's no meaning in calculating correlations with the exponential. So, like, I mean, it's not consistent.
I love to do useless things. So let me do them. No, that's a very good point. So the thing you're saying makes total sense. Why compute this higher order term? We threw away zillions of terms in the Hamiltonian, in particular terms that oscillated. The difference is that the terms in the Hamiltonian were integrated over x, and therefore their oscillations in the integral gave 0. Here I'm computing just a correlation. So I'm not integrating, and I might want to have the part corresponding to this oscillation. Now, your point is well taken. How much the thing I threw away in the Hamiltonian might modify this. But let's backtrack for the moment and come back to this. Are there questions on this? Okay, so let's finish now the calculation. So if I look at the calculation of delta rho, x and tau 0, 0, you see that I will have a part which is essentially the second derivative of the previous field that I have. Because, of course, if I have grad x1, grad x2, average of phi x1, tau 1, phi x2, tau 2, I can also rewrite it as grad x1, grad x2 with a minus sign and probably a 1/2 factor of the average of phi x1, tau 1 minus phi x2 tau 2 square. Because the part here, when I expand the square, which only contains x1, go away when I differentiate with respect to x2, and vice versa, so only the double product stays, and so I can do it. I know that this is a log, because I just computed it, so when I differentiate twice, I get 1 over x squared. So this part, which is the part coming from the grad phi, behaves as 1 over x squared. I can give you the precise expression, which is what I will do. So let me write it now seriously. Delta rho x tau, delta rho 0, 0. So this, I have, of course, a part which is k over 2 pi square. Now the coefficients are supposed to be correct. I get u tau square minus x square divided by u tau square plus x square square. And this is the part that is coming from the gradient. Now what happens with the part which is coming from this thing? So you see that I get a part which is oscillating. I will have the corresponding part with a minus sign, and this is exponential of minus log times the coefficient. And so you can work it out. So I will have some amplitude, which depends on the ultraviolet cutoff. Let's call it A lambda. And then I would get something, I write it dimensionally, alpha over square root of x squared plus u tau square to power 2k. And then if I look at the next coefficient, essentially I get the square of this. So I get 4 divided by 2 times k. So here I would get 16 divided by 2, so this is 8 k, and so on and so forth. So I would get plus, so this is a lambda 1, I would get a lambda 2 times alpha divided by square root of x squared plus u tau square, cosine of 2 pi rho 0 x, to the power, and I think it's 8k. I get cosine of 4 pi rho 0 x, and you can continue the series if you want. So this is a remarkable result, which we computed with this Gaussian thing. So what does it say? It says that first there is a part which is decaying as 1 over x squared. So this is a universal decay. This is something which is quite regular. Okay, let's do tau equals 0. Let's do the equal time correlation just for simplicity. It's decaying as 1 over x squared with a prefactor which is totally controlled by this dimensionless number, which is k. Fine. But then there are parts which are much more interesting, which is this part. So what does this part mean? It means that the density fluctuations are oscillating with a period 2 pi rho 0 x. This is exactly what you would expect in a perfect crystal. In a perfect crystal, you would say, my particles are forming a perfect object. So if I have a particle here, I know exactly where the particles are. So I would expect the density, so let's say I fixed here the fact that I have really a particle at that point. So let's say delta rho 0, 0 is 1. I know exactly where I should find the other particles, and this is given by a sinusoid, which has a maximum every time I get a particle, which is exactly what this cosine here is doing. It becomes maximum again every time I get a particle. So in a perfect crystal, the amplitude of this cosine should be constant with distance, should not decrease. Of course, here the particle move, fluctuate, so the further I will go away in space or time, the more the amplitude, this correlation, will sort of get scrambled. And the way it's scrambled is given by the prefactor here. And you see, it's scrambled extremely slowly as a power law. So I lose the perfect crystalline order, but I don't lose it exponentially fast. I lose it relatively slowly. I lose it as 1 over x to power 2k. There is the same effect for the next harmonic, except the next harmonic is decaying even faster with a higher power. So there are 3 important points here. You see that if k is small enough, this term can perfectly dominate compared to this term. Let's take k equals 0.1, for example, and remember, k that I computed is 1 over square root of u. So you could say if I make my interaction super strong, well, I will get a super-ordered crystal, because this thing will decay very slowly. This one is hopeless. It decays always as 1 over x squared. But this one, if I make my interaction super strong, you would say will decay very slowly, which means I will get a perfectly nice ordered crystal. So this is reasonable. This is consistent. It also tells you that although there are all the harmonics, and of course if I do k equals 0, you see that all this harmonic will reconstruct the perfect delta function. It tells you that if k is finite, you lose the other harmonics much more rapidly. So the dominant oscillation will be produced by this one, and this is a subdominant decay, and so on and so forth. So you shouldn't worry too much about the higher harmonics. And the third result, which is absolutely crucial, is that all these exponents are controlled by one number. One single number. Which is a remarkable thing. Imagine you compute dozens of correlations, you would say, I should get dozens of different exponents. Here, what this theory would tell you is the fact that you just need to know one number, and you can control all the decay of all the oscillations in the density. Which is something which is potentially testable. You could take an experiment, measure the density, do the Fourier transform, see that you have peaks at these various harmonics, and then measure the decay of these peaks with distance and decide how that it's indeed controlled by a single number. So this is a testable prediction. We'll come back to it in a moment. Let me go to Fourier space. If I do the Fourier transform of this correlation function, let's call it chi of x and tau, I can go to the chi of q and omega n, to which I can go to the retarded correlation, chi of q and omega, and the imaginary part of chi of q and omega is again the so-called spectral function. It's not the same spectral function we were discussing, but it's the one this time that describes the density fluctuation. It's essentially something which is the sum over n and m of exponential of minus beta en, where n are the exact eigenvalues. Then I get a density fluctuation which couples to the state m, modulus square, delta of omega plus en minus em. And then there is a factor which is 1 minus exponential of minus beta omega, which is not really important. And this is the imaginary part of chi retarded of q and omega. This is the so-called Layman representation. This is computing this by inserting an exact basis of eigenstates. The point I want to make is that the imaginary part of this thing tells you what are the excitation spectra of your system, and of course somehow depends also on the matrix elements that couple the eigenstates. So having a slow decay in real space means that you get low energy modes in Fourier space. So if you do the Fourier transform of this, you will get low energy modes around q equals 0. You will get low energy modes around q equal 2 pi rho 0. you will get low energy mode around 4 pi rho 0. So if you were plotting in an intensity plot this imaginary part as a function of Q and omega, so the color means the intensity, I would get some low energy mode around Q equals 0, and that one is easy. It's the sound mode. It's the mode that corresponds to omega equal U times Q. But then I would get also a low energy mode around 2 pi rho 0, which means here I would get some continuum of excitations. And trust me, it's bounded by some linear part. And how I connect this is, of course, a sort of question mark. But I would expect that this part controls the decay of the Q close to 0 part. These parts control the decay around 2 pi rho 0. I have one around 4 pi rho 0, and so on and so forth. Okay? So same thing here, and so on. But the faster is the decay, the less spectral weight you will get in this thing. So the spectral weight here is lower, 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 and so on. Okay? So this is what you would expect for this correlation. Are there questions on the density-density correlation? Because this is the important, this is one important thing. I will show you results from Better and That, wonderful results where this has been computed exactly, and we can compare. No question? Okay, let's do the last correlation. So let's do the average of psi of x. So what is the average of psi of x? This is essentially rho 0 to the 1/2 exponential of I theta of x. And again, if I do this, it's rho 0 to the 1/2 exponential of minus sum over q and omega, 1 over q squared plus omega squared. So this is exponential of minus infinity. This is 0. So there is no average of the single boson operator. My system is not a superfluid. Meaning, it's not a perfectly ordered superfluid. I don't have the possibility to break the phase symmetry here, and there is no way my system can acquire a global phase in its totality. Because of quantum fluctuations. I'm at T equals 0 here. I'm not talking about finite temperature. The quantum fluctuation prevents me from breaking the continuous symmetry, which is the phase rotation of the wave function. But I can compute the correlation function. So if I compute the correlation function psi of x and tau, psi dagger of 0, 0, and I will just write the first harmonic. So the first harmonic is proportional to rho 0 times the exponential of I theta of x and tau, exponential of minus I theta 0, 0. And again, I let you do it as an exercise, but using the formulas from the Hamiltonian, it will give essentially, again, exponential of 1 over 2k log of whatever, square root of x squared plus tau squared. So this is decaying as a power law with, again, an amplitude which depends on the cutoff. So, I don't know, A theta, which depends on the cutoff of something which I can write as alpha over r to the power 1 over 2k. So you see again something, and there are, of course, higher harmonics, which I'm not computing, which will mix the phi and the theta, but which can also be computed. Okay? So you see a remarkable result. My system is not a superfluid perfectly ordered, but again, the superfluid order decays very slowly. It decays as a power law of the distance, space, and time. So, should you call it a crystal or should you call it a superfluid? It has a crystalline order which decays as a power law. It has a superfluid order which decays as a power law. So it has both aspects. And now, you can call it as you want. It's called the Tomonaga-Luttinger liquid. And the system, if you want, doesn't know which side it should order. So it's like a critical system. It's like something which is at a critical point, except it's at a critical point for all the values of the interaction at T equals 0. Again, I'm not talking about temperature here. And the system has power law decay both in the superfluid order and in the crystalline order. This decay is again controlled by the single number k. Yes?
I missed the point, but why do you have rho 0 and not rho x there?
No, because I use the formula, that's a good point. I use the formula that I gave you for the field, psi, if I can find it, which is the interest in keeping it here. So now here is my dictionary. My dictionary is that psi is square root of rho exponential of I theta. So I keep the first term in rho, which is rho 0. Then I would have the other term, the grade phi, the exponential, and blah, blah, blah. This term I didn't compute. So I just replaced here rho by rho 0. Okay. And a priori, that will be the dominant term, because every time I will add a field phi, it will contribute to the decay. Okay. So I'm sort of giving you the leading term in the decay. Every time you have a field phi, as you saw here, and it appears with a larger coefficient, the exponent that comes out is larger. Okay. So that's the dominant term. Okay. Keep in mind, just as a rule of thumb, k is 1 of u. Square root of u. That's what we obtained. Now, you could say, but if k is 1 over square root of u, when u is super small, k is very large. And then this decays very slowly. And on the contrary, the crystalline order decays very rapidly, because the exponent is 2k. So if u is super small, a good superfluid, because the dominant decay is given by this correlation. So you could say it's more superfluid than crystalline. On the other hand, if u is super large, k is very small. And then this decays super fast. Well, it's still a power law. It decays with a larger exponent. So you could say it's more crystalline than superfluid. So again, you get power law every time. But if you had to write not a phase diagram, so this is like, let's say, this is u. So if u is 0, and I would say infinity here, and I put quotes, you will see why. I would say k is infinity here, and here, let's say it's 0, with a question mark. When I would say it's more crystalline than superfluid? Again, it's not a phase diagram. I have power laws all the time. But when would you put the, not transition, but the fact that you rather call it a crystal than a superfluid? Yeah, so you have 1 over 2k, which should be equal to 2k, so k equal 1/2. So when k equal 1/2, you would say here it's dominant superfluid, and here you would say it's dominant crystal. Okay? But again, it's power law all over the place. So this is, again, an extremely powerful, testable prediction. Because you can say, let me measure the psi-psi correlation. Extract the exponent. Let me measure the density-density correlation. Measure the exponent. And normally, these two exponents must be inverse, one from another. Which is a highly trivial prediction. Okay? Now, how could I extract the psi-psi? Let's do the Fourier transform. The Fourier transform is usually done with the, for example, only in space. You measure the equal time correlation. So this is n of k, the momentum distribution, is the Fourier transform of psi dagger of x, psi of 0, exponential of I kx. This is the Fourier transform of the distribution, and it gives the momentum distribution of the system. So let's do it by simple dimensional analysis. This is decaying as 1 over x to power 1 over 2k. So this integral is behaving as x to the power 1 minus 1 over 2k, and x has the dimension of 1 over, I should call it q to be consistent with my previous notations. And x has the dimension of 1 over q, so I expect n of q to be behaving as q to the power 1 over 2k minus 1. You can do the integral cleanly if you want, but it's a power law, so I can do dimensional analysis. Now, what does it mean? If I had a superfluid, a true superfluid, this would tend to be constant at large distance. So for a true superfluid, psi of x, psi of 0 tends to a constant when x goes to infinity. I have perfect order. I can decouple the average of the product, and that's the square of the average. But then when I do the Fourier transform, I have the Fourier transform of a constant. The Fourier transform of a constant is a delta function in Q. So the Fourier transform tells that n of Q has a part which is a certain constant times delta of Q plus regular terms. So it means that my occupation number, n of Q, as a function of Q, has a delta function peak at Q equals 0, plus whatever here tails I need. This is a true superfluid. I get a delta function. I have a macroscopic occupation of the mode at Q equals 0. Here, because it decays, I don't have this, but what I have is an n of Q, which is behaving as a Paolo singularity here around Q equals 0. So this is divergent as Q to the power 1 over 2k minus 1. It's divergent provided that k is larger than 1/2. Okay? So I can again say if I want to view this as a superfluid, I don't get the perfect delta function here, but I get something which is still divergent at Q equals 0 and which shows that my system would like to become superfluid, but it can't.
Sorry.
Yeah.
We saw that the spectrum is indeed Logarithmic spectrum.
Yes.
So, I mean, if we want to define superfluidity by Landau-Kloof criteria, we always have superfluidity.
So that's a very good point. It depends what you call a superfluid. When you are in high dimension, more or less, the fact that you get an average of psi, that you get a spectrum which is linear, you all call this a superfluid because one occurs when the other is occurring. In 1D, it's a little bit more subtle. You can get a linear spectrum, which based on Landau criterion, you would say it's a superfluid. But okay, is Landau criterion really foolproof? But if I measure the average of psi, I find 0. So if you use this as a criterion, you would not call it a superfluid. So this is here what people call quasi-long-range order, another use of the word quasi, which maybe we shouldn't, just to say that the system is a little bit in a more subtle state than a brute force object. So when I say it's a superfluid or it's not a superfluid, I would have to qualify what I use as a criterion, because now these criteria are disjoint. If I use the criterion average of psi, 1D is not a superfluid. If I say I should lose the psi dagger exponentially, it's always a superfluid because it's a Paolo. If I use the criterion on what is the dominant correlation, it's a superfluid down to k equal 1/2. If I use the fact that I want robustness with respect to disorder, for example, I should solve the problem of 1D bosons plus disorder and then decide if I get perfect conductivity or not. So now I have to be much more careful on what I call a superfluid. So here I use the fact that if I look at n of q, I would say I have a divergence around q equals 0. It's not a delta function divergence, but it's still a Paolo divergence. So this would say the system would like to become a superfluid, but it can't. Okay. So we are left with 5 minutes, so or so, maybe 10 minutes. So now the question is nice. I show you that you can compute a lot of things, and of course it's not limited there. Give me another correlation, I will compute it. I have a Gaussian field. You know, it's just turning the crank. You give me something, I can compute. Again, we have fully solved. When I say fully solved, I mean we have the low energy properties of interacting 1D bosonic systems. That's very nice. I'll show you tomorrow that you can do spins and fermions exactly the same way. Now, why I say interacting bosonic system? Because I took a local interaction, but I could put any interaction I want. I just replace rho by the expression in terms of phi and whatever, and it doesn't change very much. If I go in Fourier space, I would get sum over dq, u of q, rho of minus q. So if I want to replace by rho of q by 1 over pi, or rho of x by 1 over pi grad phi, I would just get u of q times q square times phi star q, phi q. So I just solved the problem where u of q was a constant, but I could also take u of q, which has a spatial dependence. Doesn't really matter. So I could add now every term I want. You give me a term in boson language, I add it to the Hamiltonian. Doesn't mean that all Hamiltonians will be quadratic, but at least I got technology now to do it. The price we pay with this is, of course, we're limited to low energy. And low can be very low, because if the interactions are super weak, well, my linear spectrum that I am very proud of here will have a cutoff which will be super low. So I'd better not excite the system at energies which are larger than this cutoff, or I will need the full solution. So that's where exact methods, or maybe numerical methods, have definitely an edge on the field theory. You would need to go to extremely large distance to get the theory applicable. But we have also a certain number of things that we are not necessarily very proud of. We have unknown amplitudes. And I told you to keep me on check, but I'll do it myself. We have thrown a lot of terms in H. So one very natural question is, how much of what I just told you has been a waste of 2 hours of your time? Because at the end of the day, it's not anyway correct. And that's essentially the situation that was the case up to the beginning of the 80s. People thought that these bosonization methods were good indication of the qualitative physics, but at the end of the day, not much more. And things changed with the paper of Haldane, where he introduced the concept of TLL, Tomonaga-Luttinger liquid. And so the answer is, what we did is exact, provided that one use the exact values for U and K. So in other words, the claim of Haldane is that the quadratic Hamiltonian that I explicitly derived for you, but by replacing and throwing terms, is actually the exact fixed point Hamiltonian which will describe the low energy physics of the problem. And all the rest is irrelevant operators that I can safely throw away, but of course these irrelevant operators will have an effect. And the effect is that they renormalize the coefficients in this Hamiltonian. So what is wrong in what I told you is not the expression of the correlation function. Of course, the amplitudes are still non-universal. They depend on the cutoff procedure or whatever. There is nothing I can do about it. But the exponents are exact. The relation between the exponents are exact. But I cannot use reliably the perturbative formulas that I gave you for U and K, because this one have been derived by throwing away all these terms. So these perturbative formulas are probably not too wrong if U is super small, because then all the other higher terms are giving super small correction, but will become completely cuckoo if U becomes very large. But the claim is that I can still use my Hamiltonian, I can still use the representation of operators, but I just need to find a trick to inject in this Hamiltonian and the right K. Yes?
Is it just a mere statement then of Landau's where like you again have a normalized mass, but then you still obey like the same?
Exactly. So it's the 1D equivalent of Landau Fermi liquid theory. It's even better because in Landau Fermi liquid theory, technically you have an infinite set of parameters that you should determine, which are the Landau scattering coefficients. So not just the mass, but many others. And once you have done that, the claim is that all the structure of the theory is okay. For Luttinger liquid, it's exactly the same, except you need 2 parameters. And because you need 2 parameters, and I would say there is another analogy. Fermi liquid theory was invented by Landau. Tomonaga-Luttinger liquid was invented by Haldane, so none bear the name of their inventors. So maybe it's also a connection there. But the point is, again, you have to find a way to exactly compute U and K, or extract U and K from experiment after all, you can do 2 experiments, measure these 2 parameters, and then you get predictions for all the other experiments. Okay? There are other consequences that we will discuss tomorrow, finite temperatures and so on and so forth, which are a straightforward consequence on the conformal invariance of the theory, so this is not. So do you see a trick one could use to extract exactly these parameters? I cannot do perturbation. Whatever works. Compute any quantity that you know how to compute by your exact method. For example, specific heat. Specific heat is proportional to T over U. If you can compute from better ansatz the specific heat, you get U. Finite size, dependence of energy. E of L minus E of infinity divided by L square is proportional to something called the central charge, which measures the number of massless mode, which is 1. And then there is U, and then you get U. Response to a twist in boundary conditions. So if you impose that psi of L is exponential of I phi, okay, it's not the same phi, I nu times psi of 0, then the second derivative of the energy of the ground state with respect to nu square is proportional to U times K. Compressibility. The inverse compressibility is U over K. And so on and so forth. The idea, just compute something with bosonization, and then compute something exact with either better ansatz, if you can do it, ansatz, or numerics. You see that this is a remarkable technique, because numerics to give you correlation on a side chain will lead to a disaster. But it's certainly very good to give you the compressibility. In D, 40 sides, so the finite sides are negligible if you want a global quantity like compressibility. Just add one particle, remove one particle, get compressibility. If you do a twist on the boundary conditions, Giamarchi, because you usually work in a box, but easy to do with Monte Carlo or exact diagonalization, finite size effects are super small. So computing directly the correlation function is hard, but computing the compressibility or the response to a twist is a moderate numerical effort. Same thing for better ansatz. Getting the exact thermodynamic equation is hard, but you just compute better ansatz for 100 size, 200, you will get an excellent approximation of the compressibility. And you just need 2 of those. So that's what I meant when I showed this diagram, which was to say that you make the methods work where they are strong. If you want short distance or exact answer, better ansatz or numerics. If you want to address very large distance, correlation functions, complicated correlation functions, finite temperature, which we have not seen, but we will see is directly solvable. Well, it's a Gaussian theory. You can compute directly at finite temperature. Then what you do, you take first the better ansatz or the numerics, depending on whether your model is integrable. You determine the U and K from easy quantities, and you inject in the field theory. And that's it. Problem solved. And if you need something short distance that the field theory cannot give you, you use directly the numerics or the better ansatz. So at the end of the day, we have the ultimate weapon, which tells us that by combining better ansatz and numerics, we get the short distance property, and we get the input parameters, the exact input parameters that we need to put in our field theory to go beyond and get the large distance property. So this is an impressive achievement, which was done by Duncan, which is to say, that's why I was saying he didn't get the Nobel Prize for that, but he could have gotten it also for that, because it gives really a very efficient tool to compute using the field theory and to compute exactly, essentially exactly, the correlation functions. You can even do better, and I will end on this, the amplitudes. What do we do with the amplitudes? Well, the amplitudes, they are non-universal, but you can do the same trick. Compute a relatively simple correlation function. For example, equal time, which is usually more easy. And you compute it numerically. And then you would find that numerically it decays with a certain amplitude A1, and then 1 over x, let's say, to some power. Well, compute it by the field theory with a cutoff procedure, and then you would find a cutoff A lambda, and then alpha, which of course is a function of lambda, divided by x with the same exponent. Well, match the two results at short distance. Relatively short distance. 5 sides, 3 sides, 10 sides. Something which is human. You don't try to compute the asymptotics. You just try to compute intermediate range. And it gives you an exact calculation of the amplitude. There are, from better ansatz, beautiful calculation by Lukyanov and Zamolodchikov to give you the amplitudes for specifically integrable model like XXZ chain, which gives you specifically this amplitude. Of course, instead of doing numerics, you can also do better ansatz and get these things. There are also exact calculation for some models of nearest neighbor, next nearest neighbor, next nearest neighbor correlations, which have been established. So whatever works, you can now complement the field theory by using, again, the two other methods, which gives you the short distance physics exactly, not only to get the exponents, but to get also the amplitude. At the end of the day, it gives a power to your field theory, which makes it exact practically immediately. And as I said, when it stops to be exact, you even have direct numerical or analytical techniques to start with. Okay, so I'll stop here. I think we've made the tour, an essential tour of what is the bosonization technique, what is the methods that I can use. So tomorrow what I will show you, which is of course important, is that it works. So I will show you experimental realization and test of this theory, because that's important. And then I will also show you that we can extend this method in a very trivial way to finite temperature, spins, and fermions. And then you will have the full picture of everything that works. And then we'll start things which are more complicated. Because, of course, as I told you, if all problems would be solved by this theory, we would be out of a job, which is not the case. So then, of course, not all models can map onto this theory. And the interesting physics is now happening with models that cannot be mapped. Okay, I'll stop here, and we continue tomorrow.